All right, let's get started. Okay, so I guess last time we talked a little bit about this out-of-order execution that's going on in the CPU. This is how the CPU is able to run so quickly. I think probably the most important part of this out-of-order execution has to do with memory access. So much of what a program does is just retrieve things from memory, and that can be really slow. Depends a little bit on the current state of the memory. There's a kind of a tall stack of components that together form the memory hierarchy. And yeah, perhaps we better start by reviewing that. So in terms of just addressing normal memory, so let's ignore any sort of I/O here. We're not talking system calls, we're just accessing memory. What are some aspects that could sort of impact the performance of just a move? So it's an assembly instruction move, and how long is it going to take? Right, so let's see. Waste, no. Okay, so why don't we start with some guesses? Actually, I was recording the right video. Yeah, it was showing up there. Yeah, okay. Any guesses? How long does a move take? In cycles? One cycle, okay. So we have one guess for one cycle. We have one for 10,000 cycles. Any other ones?
Are we just talking about moving between registers? We're not talking about memory at all here?
No, just in general. So, okay, what's that? What? We got a 15?
No. Ignore me.
It's actually not.
15.
It's not all bad.
I'll take 15.
You'll take 15? Okay. Yeah, one. Yeah, okay, that's fine. In fact, I think we looked it up in the Agner-Fog reference just last time, and it wasn't even one cycle. It was like 0.25 cycles. But so one is a good guess. 10,000 is also good. Any other guesses? We're off by some. I mean, so of course it's going to be a range. But I'd like to try to get at least some more of the possible values here that are reasonable. I think 0.25 is a good one. But of course, you could also count that as... okay, actually, let's leave it like that. 15 is good. A million. 1 million. Let's see. Okay. I don't really mind that. That's fine. I think we're missing one highly relevant one. We're missing the DRAM access from actual memory. Probably gonna take us maybe call it 400 cycles, maybe something like that. Okay, so I think that these are actually all legit values. So let's start thinking about why. So this 25 cycles, this would be move from register to register, or move immediate to register, right? So moving an immediate to a register, that's an actual value, right, of a 5. Put 5 in the register. Register to register, that actually isn't an instruction. It looks like an instruction, but it isn't executed by an execution unit at all, because it's just a question of renaming the register. So it ends up kind of, there's some steps in between here. Maybe we'll look it up in the optimization manual. There's many steps in between, but one of those steps is just eliminate any of those move things, because there's nothing to do. Just do the reassignment in this renaming buffer, and we're set. Okay, let's see. What could take 15 cycles? I think we're missing one very important one. I want to call it 3, I think it is. 3 or 4. This is moved from L1 cache to register. Or the other way. It's the same read or write. So 15 cycles, you know, I think maybe on my CPUs that I've been testing on, maybe it's more like 10. So that's a L2. So if the value, if the address you're trying to address at the moment happens to be present, there's a copy of it present in your L2 cache on the core that you're running on naturally, then it might take 10 cycles. We're missing another one. I think something more like 30, 40 cycles is if we're in the L3. So the does anyone know how big an L1 cache is? What was that? 64. So there's cache lines. Those are 64 bytes. So actually the granularity of the cache, anything the cache does, is moving 64 bytes here and there. It's evicting or loading 64 bytes. You try to load 1 byte, well, you get 64 bytes for free into your L1 cache. Everything goes into the L1 cache, and then maybe you move a 1 byte into a register. All right, so that's 64 bytes of each cache line. But then, how many of those can we fit in an L1 cache? What's that again? 6 megabytes in the L1. Oh, I wish. Yeah. No, it's. I think on the ones I looked at recently. Why don't we check that out? So we'll go to my Linux machine. It's like DM decode. DMI decode is a cool little thing, and that'll say things about what's in. There's all sorts of types you can ask about like that, right? But we're interested in the cache at the moment. Oh, it's really screwing this VM. I don't know why it looks so weird in the VM. Let's. It looks like there's hundreds of caches. Something is really wrong. Let's do it on here. All right. Okay, so the L1 here, and please let me know when things are too small to read. Our L1 cache, ooh, pretty big. That's pretty big on this machine. Okay, interesting. I expected 32. Wow. Okay. Yeah. This also is way off. Okay. I don't know. Maybe we can't trust these values. 512 kilobytes. That's crazy. But maybe. Okay. Anyway, I have some measurements we can make in a little bit and actually figure out what the sizes are. I don't believe this number. I think there's something funny with it. Maybe it's not. Maybe we're looking at the wrong one, but it certainly looks like L1 cache. Anyway, okay, so I think for now, let's just use my working assumption here that it's actually 32 kilobytes. I think there's something wrong with a half a megabyte, but we'll see. Okay, so if your working set, that is the cache lines that you have been touching, are together form only 60 or 32 kilobytes of data. That is your moves. Instructions have a separate cache. Let's ignore instruction cache for now. So just any moves you're making are touching a total of 32 kilobytes only. Then, as long as we're running on one core, your entire program will be accessing stuff from L1 cache, and every move will take at most 3 to 4 cycles. That would be awesome. There's some restrictions, of course. There's the granularity of 64 bytes. So you can't use bytes scattered all over memory. It would have to be more or less contiguous for this to work out. So there's about, what is there then? 512, I would think, cache lines like you can fit in your L1. 512 different 64-byte chunks, right? 512 times 64, 32 kilobytes. Okay, so that's going to be fast. And then one step out, this L2 is just a little bit bigger. That also belongs only to this one core. That's probably on the order of, last I was looking at it, I think it was 256 kilobytes, but now I'm doubting myself with these numbers. I think the reference I was looking at least had that. Okay, so that's considerably bigger, but not enormous. Yeah.
Are these per core measurements?
Yes, the L1 is per core, the L2 is per core. They each have one little one. In fact, I had a picture of this. Let me see if I can pull it up immediately now. I was just doing this meet and greet the other, no, not meet and greet. Where is it? Where was I presenting this? Oh, it was just yesterday. I should have it. There, okay. Here it is. Okay, that's what it looks like. Right, so a chip, you open it up, it looks like that. This is the sort of the CPU where all the business happens. And then I think part of this, maybe this is the L1, that's the L2, something like that. And this is an L3. It's actually little pieces, but they're all shared between all the various cores. This is a core with, I don't know, 16, 20, a chip with 16 or 20 cores. So this is sort of a schematic that is equivalent to this. You can kind of see it. Like here's all the logic, and then the cache is next to it, and then there's some buses going around like this, connecting it all. Kind of looks the same. In fact, this even is the same, the right number, I think. It's pretty nice. And then there's some logic for I/O, for talking to memory, and for talking to PCI buses and all that stuff, and that'll be on the edges. But that's an aside. All right, so what was I talking about? Oh yeah, so this L2, basically it's just a slower but bigger version of the L1. Not much else to worry about there. Both of these are 8-way associative. I think we can ignore that what this means for now, but it can have some really curious effects. If you access memory only sort of at, let's say, at 8 kilobyte boundaries, like access one byte at first 8 kilobytes and another byte at another 8 kilobytes and so on, and you keep going, then you can get some really strange effects where the cache is full even though you only are accessing 9 pages. Right? You keep losing cache entries even though you're only accessing, sorry, not pages, 9 cache entries in the end. That's associativity, but maybe we'll skip that for now. Okay, so L3 on a normal multi-core CPU, which is what we're interested in this class, the L3 is shared between all the cores on one chip. So it's almost like main memory in a sense. There's some contention for it. If you want to, it's not clear that whatever is in L3 is yours to write in. It's just a sort of a fast memory that you can load elements from. L3 has some other duties too that we can talk about later when it comes to multi-threaded processing. Okay, so if your access tries to do the L1 and that fails and it tries to do the L2, I think the 10 cycle includes this. So it'll take 10 cycles then, maybe something like that. And if it's not in there, it'll look in the L3, and if it's not in there either, well, then we have to go and look in memory. So just loading from RAM, and this varies quite a bit. At least on a larger system, maybe I'll go back to that. Oh, did I close it already? I'll open it again. On a larger system, it looks more like this. So here's one of those chips, and then you have some buses in between them. And so from each one of these chips, you have those memory buses. Memory, like a bunch of pins. It'll be maybe 128 pins going out from the chip and connecting to your little DRAM sticks. Many of you have probably seen what they look like. If you haven't ever opened up a computer, I highly recommend doing that. Not your laptop though. You'll lose the screws. Here, why don't we do a 4-socket motherboard, just to get a feel for what's going on, in case it's not obvious. Okay, so it looks like this. Oh, that's really small. Okay, so the chips aren't on here. Those are just sockets that you put the chip on and clamp it down. But basically here is room for 4 different chips. And then each one of them has a bank of these slots where you can put a little DRAM card, which has 16 gigabytes of memory or something. So you would put one here, you put one. Let's see. I don't know. There ought to be 8 of them. Anyway, so you give a little bit to each one of them. And so if the memory is right next to the socket that your core is on, it'll be faster. The address that you're talking to, it comes from some memory. Like it has a physical location, and it might be hanging off of here. If we're running on this and it's hanging off of the bus here, well, that's going to be faster than if you're trying to access memory that's hanging all the way up here, because then you have to send a message over this bus to ask this one to send the message to the next one, and so on. So that clearly can add quite a bit of latency. This is called non-uniform memory access, I suppose. Anyway, it is still shared memory. The moves look exactly the same. It seems like it's all one big piece of physical RAM, but as usual, you find that the abstraction breaks once you start making performance measurements. So if we want this to go fast, probably you'll want your memory for whatever you're running here, you'll want to allocate memory from the local memory bank. There's special memory allocation methods for this called libnuma. You can look into it if you're interested. But it gets kind of weird because maybe you're running here for a little while, you allocate memory here, and then the CPU scheduler, the OS scheduler decides that, oh, this processor doesn't have enough to do, so let me move your processes over to there. And now suddenly you're doing all remote memory accesses. So it's not something you can just rely on. You'd have to think carefully about what you're doing. But hopefully we'll get a chance to play with that later in the semester. Okay, so where were we? RAM, right. Okay, good. 10,000 cycles. Probably it's a little low. But we may, I don't know if I could do that. But something in that order. Maybe it might be 50,000 cycles, but something like that. Any ideas? When would a move take 50,000 cycles? SSD. You can't move from SSD, can you? You have to specify a memory address. Page fault, exactly. All right. So if you malloc something large, generally speaking, the libc malloc at least will use the system called MMap. It's not going to raise the break and the way you normally expect. For large things, it'll use MMap so that it has an independent memory region that can be freed without worrying about whatever is on top of it on the heap. This makes sense. In any case, MMap tends to be lazy. That's the standard implementation of MMap. It says, yeah, fine, here's your memory range of virtual addresses, but it doesn't actually allocate any memory. Maybe it kind of remembers that, oh yeah, I promised this process so much memory, so it doesn't overcommit, but it doesn't go and add page table entries to for all of the gigabytes that you asked for. Okay, so what happens then? Now you have all these invalid page table entries. Anyone not familiar with page table entries? Okay, good. We don't need to have an intimate relationship with those. We can just kind of have the general idea of virtual memory and we'll be fine. But here we have a page table entry that says there's nothing there. So the CPU throws a page fault because there's no way to continue executing. The page fault is an interrupt. The OS starts running, right, the interrupt handler, and now we have to do something about it. There's basically two choices. The OS could look at the address we're trying to access and say, well, you're not supposed to access that memory, and then we have to kill the process. Processes that don't do what they're supposed to, they die. So usually if you try to access the dereference address 0, for example, you'll get a null pointer exception. That's the OS saying null pointer exception after receiving the page fault and deciding that, well, there isn't supposed to be a page at address 0 anyway. And then the OS will kill the process. So CPU isn't involved in killing the process. It just kind of alerts the OS that something's going on that I don't really know how to handle, and the kernel handles it. Okay, so in this case, if we've allocated memory, malloced a large chunk, we got a pointer back, everything's legit. We try to access this memory, but there wasn't anything there. Now there's going to be a page fault, and the OS has to allocate a page. It actually has to make sure that page is also all zeros, and then set the entry in the page table, and then go back to user space. So that's quite a bit of work. Usually it's a lot of work because Linux is just an enormous piece of software. It does all sorts of statistics and handling every little special case of everything. And so there's a lot of work involved. You want to manage the page table, you have to acquire locks, you have to do this and that, and it's a big deal. So probably doing all this in 10,000 cycles, yeah, maybe that's fine. It's something like that. Okay, page fault for lazy memory allocation. Okay, and here's another one. This one's probably your SSD. Someone mentioned SSD. So how could we end up accessing a disk? This has to be something beyond the motherboard. It's not RAM. It's not something the kernel's just doing. This has to be I/O involved to get to this kind of latencies. But okay, so what would cause that?
Read or write from keyboard.
From a keyboard? But this is a move. Move doesn't get to know about keyboards. Move says address.
Maybe if something is swapped out of frame due to.
Exactly, right. So again, we get a page fault. This time, the OS has swapped out, it ran out of memory. So it took some page of your process, it wrote it to disk, and then it invalidated the page table entry. So next time we try to access this page, well, too bad. Page fault, OS sees, oh, I wrote it to disk, so I'll have to go and get it from disk. Read it in, find a page where to put it, set the page table entry right, and read in all this stuff from disk, and then return. And it's very optimistic to be able to read anything in from disk in 1,000,000 cycles. But if you have an SSD, that's probably okay. So SSD swap in, let's say. We could just as well end up running 10 million cycles, and that might be a hard drive. And if we want to get a little crazy, can we go further than that?
Do we have like a swap file on like an NFS mount on a server someplace else?
Exactly, right. So you could, or you could also call it just distributed shared memory. That's basically the same idea, where we do a network access to get the page. And then it all depends on how long how slow the network link is. If you're out on a boat in the Pacific, it's gonna take a while. So basically unlimited. Okay, so how long does a move take? Well, it's somewhere between a quarter cycle and 10 million cycles. somewhere in that range. So we can't really be counting moves and getting an idea of how fast this program will run. We have to have a better idea of what is it we're accessing here, something about the access patterns. Right. Okay, I wrote a little program. I thought maybe we'll take that for a spin. Oh, actually, before we do that, who finished the homework? All right, sweet. Okay, I think we don't need to go through it. I made a bunch of sneaky bugs, but once you found them, it was pretty obvious, I guess. But finding them isn't necessarily that obvious. But, I'm not going to make that kind of bug again. The next homework, I think, I'm not sure it'll be bugs. I'll post it later tonight, I think. I think for that one we'll have just 2 programs that run at different speeds. They do the same thing, but they run at different speeds, and you'll have to figure out why. And then I think the next homework after that, we'll have a program that runs slow, but it's not a weird bug like that. It's an actual, like a stupid design of the program rather than adding a sleep where there shouldn't be a sleep. And you'll try to track that down. And that's going to be it for single-threaded. Okay, but yeah, I'll hopefully be able to post that tonight. Okay, so this program is called cache stress. And I was thinking we could use this to kind of probe the machine a little bit and see what it's doing, and maybe use some of our measurement tools to see what they see when we're running this. So, why is it? That's better. All right. So I think we'll run this on the server. Let me just make sure I have. Yeah, cool. Okay, so this program, it takes 2 parameters: the size of some piece of memory, and then an interval of an access interval. And the whole thing it does is just start at the beginning, access the first byte. Actually, I think it reads the first byte, and then it adds that interval and reads that one, and so on. And quickly just runs through the whole thing around and around 10 million times. Like, no, it doesn't go around 10 million times, it does 10 million accesses. But 10 million is enough that we're going to go around a few times. All right, if you haven't seen this stuff, get opt. Now is a good time to look at it. Highly recommend it, very easy to use. You get nice command line parameters. Here I'm just saying the size and the interval, and I'm doing some testing just to be very nice in this program, to make sure I have the right values. Okay, so what is it doing? It allocates some memory. I think that the mem set is probably superfluous because calloc should be doing it anyway. I can drop it. Calloc sets it to 0, that's the whole point, and malloc doesn't. Oh, no, I remember now. I was a little concerned that calloc might still be lazy. Because it sets it to 0, and it knows that the kernel will return pages that all contain zeros, only zeros. And so maybe it can do it lazily. I wasn't sure I could trust it. So let's leave the memset in there. That one's not going to be lazy. Memset sets everything to 0 now. Like right. Okay, and then we see what time it is. We do our accesses. So here I'm running through, I'm calculating the new offset. That's the current offset plus an interval plus the whatever's in the buffer, but that's 0. What am I doing here? I just wanted to make sure that we read from my buffer. Every time around, we have to read the byte here. So now we're going to get a read latency, right? Some kind of read latency. Of course, it's going to be like plus the I++ here, plus the comparison, plus the branch, right? But we get some sort of feeding and the read latency. They're all zeros, but the compiler doesn't know it's all zeros. It hasn't figured that one out. I guess memset is a library function, and so the compiler doesn't know that it always sets it to zeros, so we're good this time. In general, you can't really trust that sort of thing. Okay, yeah, compiler does all sorts of weird stuff, and we'll find some of that perhaps along the way. Okay, so, right, okay, so I'm going to the next offset, which is offset plus interval, that's always 0. And then, what on earth? Well, I'll show you what it was supposed to be. It should be like this. Right, that's it. The size has to be power of 2 for this to work well. And we'll see why in a little bit. It was a weird thing I discovered last night. Should have been obvious. Okay, anyway, so we do this. We run through the entire thing, round and round, 1,000,000 times. Samples here is 10 million. And then we see what time it was, and we just print it out. Like, these are the parameters, and this is the size. So let's try running it. So it's cache stress. Size 4090. Let's just, for the heck of it, go like that. Aha. See? Always check your inputs. Wrong class, right? We care about performance, not correctness. Okay, so we had an array of size 4 kilobytes. We accessed every byte on it consecutively 10 million times, and on average, one time around that loop took 4.1 nanoseconds. This CPU runs at 2.2 gigahertz, so about 8 cycles to go all the way around. You might want to take a look at what the program does. Oh, actually, let me do this instead. The -s, it produces better output, easier to read. Object dump has all this other stuff from the libraries linked in and so on, so this is a little cleaner. Okay, so there's all my testing and things. Let's see if we can find the loop of relevance. Here we're writing something out, that can't be it. Oh, there we're multiplying by 1,000,000. That's going to be in here somewhere. Okay, get time of day. Oh, here it is. Okay, so this sort of thing you will actually have to be doing quite a bit for the next homework, perhaps for many other homeworks, just to understand what the compiler did. Because there's so many things, so many ways that the compiler can describe your program. If you don't write your program just right, the compiler doesn't actually know quite what you meant, and it'll do something that's more generic than it had to, and it'll be crazy much slower than it ought to be. So sometimes you get like a good explanation of the misunderstanding by reading the assembly. Very rarely should you be actually modifying the assembly, maybe for an experiment, but not, it's extremely rare that you want to write an assembly program. All right, so what's going on here? We're reading, like, here's the read from myBuff plus offset. All right, this is one of those. One of these is I guess this is myBuff, and RBX is the current offset. Put that in R8. And then we're adding, that's the interval, I suppose, to RBX. Aha, RBX is the offset, right? Yeah. And then we're adding whatever we read in. And then we're ANDing it with whatever this thing was. Here, size -1. And then finally decrementing. Oh, funny. I do an I++ here, but the compiler figured, why don't we decrement instead? All right. it starts with a large value and decrements, because it does the same thing. It gets a little confusing. But maybe that's a little bit faster. Maybe it's kind of, it doesn't need to compare with an integer anymore. It doesn't need to compare against 10 million. It can just see if it was 0, and there's a special instruction for that. Jump if not equal to 0. All right. Where are we going with this? Okay, yeah, so the move probably took 3-4 cycles, but then we have to do the adding. This is actually dependent adding, so those take, I think, a cycle each. 1, 2, 3, because that's a dependent and then this is independent. Right, so that's running in parallel, because we can do lots of ands. And we can do, for every cycle, we can do 4 of these simple adds, ands, ors, shifts, all of the ALU operations. So, but because these are all dependent on each other, they have to wait for one to finish before the next one runs. So that doesn't give us anything. But this one is a separate thing, so that can run separately. And this one is also independent. I mean, it depends on that, but not on these. So I think they can all run in parallel. So it should be 3 plus, that's 3. And this can run before this, or at the same time as this. So, okay, that's how you have to kind of add up the cycles if you really want to get into the nitty-gritty of it. So what did we get? So it looked to me like, okay, 1 access to L1, and then maybe 2 more cycles, and then a jump, maybe 3 more cycles.
Question.
Yeah.
When is the flag set for the jump not equal?
Oh, that was on the sub. Sorry, I should have left that up. Was it an L10? Oh yeah. So here's the decrement, and so whenever you change a register, some of the flags are modified. Yeah.
So the add and the sub are running in parallel with one another.
Let's see now. So yeah, so the move and the add, they can run at the same time.
The and and the sub, the last and the sub are running in parallel.
This and that sub should be able to, yeah, because they have nothing to do with each other.
So which one of them sets the flag for the jump?
Oh, haha, yeah, they're running in parallel in the performance sense, but in like the logic sense, they're running sequential.
Okay.
So you end up with this parallel execution with multiple states of the CPU, right? But that's fine. They just add more transistors. That's how it goes fast. Yeah, but so yeah, to understand the program, you never have to worry about this parallel execution. It always runs, as long as you have only 1 core. Then correctness, if you have 2 cores, it starts kind of leaking a little bit. This order of execution actually shows. If another core is looking at what's being written to memory, it can see that things are happening in the wrong order here, occasionally. Okay, so we were saying this and this, they're not ordered. These 3 are ordered, so that's the longest, actually, and that's ordered with this too, right? So we have a 3 cycle, 3 or 4 plus 2 more. This one is unrelated to that, but then I don't know if the jump happens at the same time. Yeah. So that probably can just keep running. While this one is still executing, it can do another jump and start the next one. Something like that. All right. So let's see what were the numbers again? 4.2 nanoseconds, right? So maybe 9 cycles is what we observed. Seems a little off. Seems like it's off by a cycle, probably. But let's not worry about it. If we wanted, if you were a PhD student in my lab and we were developing some new algorithm for a paper, we would worry about that cycle. But right now, it's okay. Cycle here or there. That's we have many, right? 2.2 billion every second on this one, and on the laptop, they have some weird frequency scaling thing. 4.3 billion per second on one core for a while. If it gets too hot, then it has to slow down, and you can't do it on more than one core. But yeah, so sometimes I see that number. If I run cache stress on my, actually, I think we can do it. I think I had a copy here. Let's see, cache stress. No. Never mind. Anyway, it does go faster. Okay, so let's try this with something different. So let's make a large. I need some help with the math. 1 to the power of 20. Oh, 1 to the power of 20. Okay, so we do a megabyte instead. Actually, let's do the cache size. We wanted to figure out how big is the cache. I think this DMI thing was lying to us. We should be able to figure that one out pretty easily. We just need to look through all of the various cache sizes. I guess we can start with 4096. 1, 2, 16, what is it, 384, 32, anyone remember? 15, 32, 768, 65, 536. This is a pain. Actually, what am I doing? We can do much better. Bash is awesome. Let's go to a megabyte, let's say. Oh, I call that I. That's not good. Call it S. S for size. Naming is important. Otherwise, you get really confused after a while. I do. Huh. Maybe I should. I was going to go with an exponent, but let's see. Megabytes. Let's go to 10 megabytes. Huh. Didn't tell us very much. Seems like no matter how big it is, we can access this memory really fast. Any ideas? Why? It shouldn't have been like that. Once we got over that, or either we have an 8 megabyte L1 cache, which would be awesome, or we did something wrong with our experiment. Oh, don't forget, this is a cache. All right, so, yeah. The interval, yeah. The interval 1 isn't very informative here, because the first time we access the memory, yeah, it's going to take a while. And then the next time, well, it's in the L1. 64 times it's in the L1. So now we're doing all these other instructions running around, but basically it's already in the L1. So any extra cost is going to get amortized over 64 accesses. There's no point in accessing every one here. We're only interested in the latency of the cache, which only happens at an interval of 64 at least. So let's do that. Yeah, so here we get a significant bump when we go from 32 kilobytes to 64 kilobytes. And it stays up there. Okay, so it looks like our L1 cache is in fact 32 kilobytes. The L1 data cache is 32 kilobytes. All right, what about this? Actually, maybe we should try one more thing. Let's use a tool. So, I mean, this could all be nonsense. Maybe it's just noise. Well, it looks kind of reliable. Do it one more time. If this is a research project, I ask my students to run every experiment like this. Each run should take at least 1 second. So for every one of these, you need to spend at least 1 second, because there's always stuff going on in these machines. Someone else logging in, hogging your CPU for a moment or whatever. So each one takes at least 1 second, and then run them 10 times and take the average and plot the standard deviation. Then you get a scientific result, but this is a class thing. So run a few times, and we see the numbers are bigger. Right? Looks pretty consistently bigger once you cross the boundary there. So I'm telling you that that's the L1 cache, but I could be lying. So we need to measure it in a little more detail. Let's try that. I'll just use the same parameters. Let's see. 32,768 and I64. Okay. Right. So we want to see, did we actually get L1 cache misses? Right. That's what we'd like to measure. We haven't really played with perfstat yet, so let's do that. If you just run perfstat like this, it'll tell you some things about the program. It's a little more heavyweight than time. Okay, so this one counts. It uses built-in, mostly uses hardware performance counters. In the CPU, there's hundreds. For every core, there's hundreds of these little counters that are there only for the purpose of measuring performance of your program. So they count things like, oh, how many times did you read something? How many times did we retire an instruction versus speculatively execute an instruction? How many cache misses did we have? How many times did we do this and that, right? There's a crazy number of these performance counters for the various little details that we don't even know exist in the off-core. That is the part that manages communication between the various cores on a CPU. Lots of sort of undocumented stuff, and it changes for every architecture. But some things are there in common. Of course, page faults. That's not I don't think that's a CPU counter. Well, I suppose it could be. Context switches certainly is not a hardware counter-based thing. This comes from the OS. It's not a CPU primitive. Okay, so we ran for, oh look at that. It's kind of cheating us on the clock efficiency. I don't know why it would be doing that. It should be 2.2 on the CPU, but maybe it's like, it was on a, I don't know, energy saving mode or something for a little while before it spun up. Okay, so we got to run 59 million instructions. That makes sense. We were going around 10 million times. Most of what we're spending here is on just going around this thing, and there was, what, 8? Probably 6, 5 or so instructions in this loop that is executing. Okay, so we didn't get very many instructions per cycle. And that's because we're doing so many moves. These moves are what's holding us up. And I think we ought to be able to read that as probably these stalled cycles. We couldn't do anything more. This is the scheduler, the instruction scheduler, trying to find another instruction that it can push onto one of the execution units. But there wasn't anything it could do because it's waiting for a dependency, the move, right? Reading from that buffer. All right, but we were looking for L1 cache misses. So we can tell stat that we want, let's see. I don't remember what it's called, perf list. Okay, so these are only a small number of the counters, some that are documented, right? There's many more than this, but they're just known by their number. So we don't care about most of these, but maybe we can find our L1 miss is what I want. L1D. Let me try again. Replacement, eviction, pending miss. Huh. Yeah, so these count cycles. I wanted to count how many misses we have. It's weird. Cache misses. So cache misses here would count all of the caches. That's not exactly what we want either. That should be in here somewhere. Miss outside to rate. What the? How is this possible? Okay, I don't know why it's not listed there. Let's Google for it. L1D cache load misses. Hopefully this one is supported on our CPU. Otherwise I'll do it on my laptop. Okay. So we tell it which, we get to tell it which event we're interested in counting with an E. And that's the one we're looking for. Okay, so here we had 161,000 cache misses. That's not bad, because we're doing 10 million accesses. So then if we go to a larger size, aha! So with a large enough working set, right? Once you get back to index 0 again, you've already evicted that value from the cache. So you're going to miss every time. So we got 10 million misses. Okay. Maybe we'll try the cache misses as well. Not a whole lot of that. And that's because we have a megabytes large L3. So everything's sitting in L3. By the time the user program gets to it. Here, I think we're only counting I would expect that PerfStat only counts in user space. And this has all been already kind of brought into the cache by the kernel when it was clearing all this stuff. I would think that's what's going on. Okay. I thought we could see if maybe we can also get to the L2 or the L3, see what's going on there. Let's see. So, hello. Maybe not. Did I somehow freeze this thing? Is there such a thing? Okay, I guess we need a new window. So then the question is, did we lose network access or did we lose frames? Looks like frames. That's too bad. Okay, well, we can continue on my laptop instead. These machines are all used for research projects, and every now and then people do things with them. I think we have an admin who was just installing a big GPU card, maybe in frames. I think he got it yesterday, so it could very well be that he unplugged it just now. And that's too bad. But we'll. How rude, yeah, exactly. You should have checked if I was using it for class. Okay. Yes, that's gone. Oh, yeah. So maybe we'll try to dig for that. And then I wanted to show you what can happen if you aren't careful writing your code. Let's see. So what was it called? Cache stress. I guess I don't have it there. Let's see. Okay, that's available. Okay, good. Aha, this one's very upset too, of course. That's great, thank you. It's trying to save to my network volume, which was on frames. Great. I think I may have to, yeah, bye-bye Emacs. This is a problem with these SSHFS. It's using this user space file system mounting stuff. It kind of plugs into the kernel. It's not truly a program. It kind of plugs into the kernel a little bit, and kernel code, generally speaking, cannot just sit and hang. You don't write kernel code that way, but if your kernel code is relying on a user program, it's fine for user programs to hang, and so you end up with the kernel hanging a little bit too, and it looks like that's what's happening here. Come on, Emacs. It doesn't want to die. Emacs doesn't even exist anymore. All right. Oh, there it is. Okay, let's try this. Nice. All right. Trying again. Is Emacs not going to start now? It didn't like that. Okay, we'll do it with everyone's favorite, maybe Nano. I always wanted to learn VI. I think every student that I see using VI, nobody knows how to use it. Like, you know 3 commands, and you keep wasting your life using this piece of crap. But if you know about 100 shortcuts in VI, which you should probably if you're a VI user, then it's awesome. Like, you don't do arrow left, arrow right to find the third F on the screen. You say just, in fact, I forget the combination, but you say 3 something, and then maybe it's just 3F, but it's not quite. 3FF. There we go. Here's an Emacs VI user. Yeah. You do stuff like that all the time. Like, oh, let's delete the 3rd paragraph from down here. No, I'm not going to go down there. I'll just. Yeah, that's awesome. If you can handle it. Command mode is not for me, I think. Let's see. So I hope I have a reasonable version of cache stress here. I think so. I'm going to use Nano. Nano is awful. But it did start. So that's nice. Yeah, exactly. I am not saying that anyone should be using Nano for this class. I think what I'm saying is use anything but Nano and VI unless you really know VI and love it. Okay, let's see if we can make this run. Oh, suspension is not enabled. Thank you, Nano. That's really cool. All right. Actually, screw it. Why don't we do it in VI? You get to laugh. It's great. I thought I only had 1 print, but that wasn't the case. Okay, so now, if you, against my advice, are using VI, and you need to compile this stuff, don't hit escape, Q, WQ, whatever you do. Right? Just hit Control-Z, and that suspends the VI process. Right? It's still alive, and then you compile it. And then you go back in. All right? If you haven't done that yet, now I just saved you like days of your life.
Or you can just do exclamation point GCC and it runs it as a.
Of course, yeah.
Colon days, it'll run it for a minute. Or you can use schema. Or you can have like 30 terminals open.
Yeah. That's what I do, usually. But anyway, Control-Z is really cool, and you can say jobs, and you see what you have running. You can say BG, but it doesn't make sense for an editor. But to start it running in the background. Right now it's not running, it's just sleeping. If you want to come back, you say FG. Okay, we were going to do something. Yeah. size in one size less than a gigabyte, maybe? Maybe 100 megabytes ought to be enough. Or whatever. 64 for now. Okay, so it looks like you see how it's faster? That's my 4 gigahertz thing going. Okay, so it looks like, again, we're hitting double the latency at 32 kilobytes. And then we're hitting something else. I don't know, maybe it's here. Well, hard to tell. I probably should run this a little longer, right? Why don't we do that? How do you search backward in this thing? Shift N.
I know it's slash.
Let's have a debate. Okay, I didn't compile it. Okay. So I guess the action is happening. Yeah, there's one here, and then somewhere around here. It's a little hard to tell, and I think the reason is that we have an inclusive cache. So the L1 and the L2, they kind of add up. So it's not a power of 2 really where the cutoff is. It's somewhere in between, but it's probably somewhere around here, right? So it looks like 256 kilobytes ish is where the L2 is at, and then I think we're hitting another one over here. So it looks like we have a 4 megabyte L3 cache on the CPU. Okay, so I had some trick to do with associativity, but I'll save that for another time. It was really hard to think about these things and get it quite right, so I gotta practice. But let's do this other thing. Here, check this out. So remember that time, it took, what, 0.8 nanoseconds or something for a small one, right? So now, instead of this weird thing, and someone will have to explain to me what I'm doing here later, but right now we'll just do like that instead. So the point of this code, right? Oh. Come on. Okay, the point of this size thing is we don't want to go accessing. Oh, actually, this one's slightly different. This one is the version that does writes. It writes to every one of these. The performance is roughly the same. But anyway, the point of this is to make sure that your offset is never beyond the size, because that would cause page faults. So, or worse, segmentation faults. The program would die. Right, so we have to have that. So this is how I wrote it initially. I got these weird numbers. Let's try it. Huh. So it suddenly is taking 8.7 nanosecond per operation instead of 0.5. What on earth? The logic is actually the same. It does the exact same thing. Let me show you another one, which makes this even more fun. Let's try this. What's a good size? There was some. That's too small. Let's do a 2 to the power of 20. There. We'll just go with a fixed size. Build it. Okay, so now it's. Oh. Yeah, ignore the segmentation faults. I don't know. I don't know why that happened, but anyway, it's a lot faster. It is correct. These are correct. I don't know what's going on with it. This value is to be the expected value. So with a fixed size, it's a lot faster, but it's still twice as slow. This is really weird. Okay, let's ignore this size change. Actually, why is it crashing? I'm using size there. Oh. Okay. Sorry? No. All right, I'm gonna delete this. Oh, come on, escape, kill. A DV. Oh yeah, that's what it is. DV. That was in nano mode. Okay, so. Should we take a look at the assembly? Because this is really weird. I'll have to compile it again, just so we can rely on this being the right assembly. And it was called L20 last time. Are we on? Ooh. Now I'm also running this on in Mac OS, which means this is built with a different compiler. So it's not going to look exactly the same as we did last time, but it doesn't matter. The numbers we're comparing were this half nanosecond versus the 1 versus, or 1 and some. So we'll find it. Where's our loop? Oh, here it says, this inner loop header. That's really nice of it. Okay, here it is. That's the inner loop. So it looks like it, so this is Clang, it's not GCC. You say GCC, but Apple thought it's pretty clever to rename Clang GCC so that everything keeps working, except when the flags are different, which they often are. So it actually unrolled the loop. Clang had different optimizations, so it doesn't go around it does the job once, and then it does another one again, and then it jumps back. So then it decrements the value by 2 every time. That's loop unrolling, standard compiler optimization trick. If you haven't taken the compiler class, highly recommended. I don't know who's teaching it next, but it's a cool class. You get to write your own little compiler. Yeah, okay, so what happened? It doesn't look quite the same. Maybe we can just look at one of these blocks. Or maybe we should look at this one where we had the add. Should we try it with the other one too? I'll just copy this into another buffer. I'll hide it in a text edit for fun. There. And then my weird incantation here. Maybe someone has figured out what it means, why it works that way. This inner loop header. Oh, that's not the one. Here. Oh, look at that. Okay, so it unrolled it a little differently. And now it does 5 at a time. So I think the compiler decides, because this is such a small thing, may as well unroll it a little more. For a long one, there isn't that much point, because basically you're amortizing the cost of doing the branch, like the decrement on the branch. And it's, if you have a long piece of code anyway, who cares about a couple of cycles? But here we do care. So that's part of it. But there's another very significant difference based on our findings in the last lecture. Yeah. What's modulo? Modulo, well, it's not a sequence. Modulo is it's basically division with a remainder. Right. So we throw away the result of the division, we keep the remainder. That's modulo. So that's how you implement modulo. you remember how long it takes to do a divide? It's like 120 cycles, 180 cycles, something like that. Whereas an AND takes 1 cycle, and you can run it in parallel with something else. So that one goes slow because it's using division. But why did it go fast when you use a constant? So it was the same code, right? I just set the size to a constant at the top.
Because the compiler can use tricks to compute the modulo also with like multiplication with the integers, something like that.
It's actually going to have to use what I'm doing with an AND, I think. But yeah, the compiler can see that, oh, they're doing modulo by a factor of, by a multiple of power of 2. Right. Modulos power of 2, those can go real fast if you do it right. So the compiler just special cases this. It doesn't need to use division anymore. It just replaces it with an AND. Right. But it only works if you know that the size is exactly a power of 2. Right? And the compiler isn't clever enough to see that, oh, the inputs will always be a power of 2, but because that's what they required at the very top, there was an if condition. It's not like that. It just sees like, oh, here's a value. Like, that's a power of 2. Let's go. Yeah.
So then why did our little like fixed size fail?
Why did it fail? Yeah, I didn't I didn't figure that out. There's some weird little bug in the little oversight of mine. I would ignore it for now, but maybe if I find it, I will look for it and I'll post it on Piazza.
There's a possibility that when we are assigning the memory, smaller size, and when it is
That's it. Right. I was changing the size too far down the program. Right. So the loop was looping over 1 million, but we only allocated 4 kilobytes. Right. So that I should have done the fixed size a little higher up. That would have done it. But anyway, so you pass in a parameter. Compiler has no idea what the number is going to be. It doesn't know it's going to be a power of 2. So if you're going to do a modulo with an arbitrary integer, you have no choice. It's going to have to be a div. Right. Hundreds of cycles right there. But we know it. Right? We know our program will only have powers of 2. I guess if you had a ridiculously clever compiler optimization phase, it could do this, right? But you would write probably thousands of lines of code to detect these cases, infer these cases, and then they never happen. Right? So now you have thousands of lines of extra code in your compiler that can have bugs in it, and it's never used. That's not really going to happen. GCC isn't going to let that in. So that sort of thing won't get provided by the compiler, but we know here that size is always a power of 2. So what am I doing here? And size minus 1. Why does that make modulo for powers of 2? This is a compiler, no, not a compiler question. This is an interview question. If you read that green book, what's it called? Crack the Coding Interview. I bet you'll find something like that in there.
You're masking out the top bit, so it's always going to be the lowest.
Yes, exactly. So modulo power of 2 is a question of just keeping some of the bits, right? Some of the lower order bits. And so I need to create a mask that has the lower order bits set and the rest of them zeros. So you could make a for loop to create this mask, right? But you don't have to. If you have a number that says like 1, 0, 0, 0, right? And you take minus 1, then it becomes 0, 1, 1, 1, 1, 1. So, and that's the mask we want. So that's the mask, and this is for any power of 2, it'll be the correct thing. So anyway, that gives us, and the compiler, of course, knows that the size is already known. So it'll compute this over here. It's not going to do it inside the loop. Right? It's common sub-expression elimination or loop, whatever. I don't remember what it's called. Anyway, you can move this out of the loop because size doesn't change within the loop, and size is a local variable. But if size was a global variable, right, then we don't know because there could be another thread changing size. So then it would have to compute it in here, and it would load size every time around. Right? So you got to be really careful about these things. In fact, I think that may be why it wasn't as fast as it should have been. Let's try this. We have 0 minutes to do it. Can I have a couple of minutes? If you need to leave, go ahead and leave. I just want to try this. What are we? 48, 576. Okay.
I have to give an extra 5 minutes.
Oh, did I do something weird? Aha, thank you. I love this thing. All right. All right, so what did it do now? Where's my loop? Here. Okay, good. So it ends it. Oh, no, that's okay. This time it worked. Okay, so that's not why it was slower. I don't know why it was slower than. Okay, anyway, I think we've learned a little bit about the caches and about the vagaries of the compiler. I'll post the next homework soon, and I'll see you on Tuesday. Have a good weekend.